Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized conversations.
Today, we're talking about robots, specifically teaching robots to do new things. Now, if you've ever tried to teach someone a physical skill like how to throw a ball or bake a cake, you know it's all about trial and error.
Exactly. You try something, it doesn't quite work, you figure out what went wrong, and you adjust for the next attempt. You don't start from scratch every time. So the big question is, can we get a robot to learn in the same way? Not just by watching a million videos, but by actually trying, failing, and thinking about its mistakes.
That is precisely the question a new paper from General Bionics Inc. tries to answer. It's called Act, Observe, Rewrite, and the name basically tells you the whole story. It presents a framework that lets a robot learn by literally being its own programmer.
Its own programmer? So it's not just adjusting a few numbers in the background, it's actually writing code?
It's writing code, real, executable Python code. The whole system is a loop with 3 steps, just like the title: Act, Observe, and Rewrite. Let's break it down. First is Act. The robot has a piece of code, its current instructions, or what the paper calls its policy, and it tries to do a task, like pick up a cube.
And like most of us on a Monday morning, it probably fails at first.
It definitely fails, and that's where step 2, Observe, comes in. When the robot fails, the system takes a few snapshots of the key moments, like when the gripper misses the cube, and it also collects data logs. It's basically gathering evidence from the scene of the crime.
Okay, so it has a file of evidence. What's next?
This is the magic part: rewrite. All that evidence, the images, the logs, and the original code that failed, is fed to a large language model, or LLM. The AI is then prompted to act like a detective and a programmer. It has to diagnose the failure, figure out the root cause, and then rewrite the Python code to fix the problem for the next attempt.
Wow, so it's a cycle. The robot tries, it fails, the AI looks at why it failed and writes better code, and then the robot tries again with the new and improved instructions.
Exactly. And this is totally different from how we usually train robots. Normally, you'd either have a human teleoperate the robot for thousands of hours, or you'd use a complex reward system where the robot gets points for doing things right. Those methods can work, but the robot's brain is often a black box, a huge neural network that we can't really understand.
But with this Act, Observe, Rewrite method, the robot's brain is a Python script. You can literally open the file and read the logic it's using. That seems way more transparent.
It's incredibly transparent, and the paper shows just how powerful this is with a few experiments in a simulated environment. They gave the robot a few tasks, starting with a really simple one: just lift a red cube off a table.
How did that go?
The first attempt was a complete failure. The robot arm moved over the cube and just hovered there. It never even tried to go down. So it went to the observe and rewrite steps. The LLM looked at the images and the code and said, "Aha! The arm thinks it's closer to the cube than it actually is. There's a systematic depth sensor bias."
It diagnosed a hardware calibration issue?
Pretty much, and its solution was brilliant. It rewrote the code and added one little line: always add a 2.5 centimeter correction to the vertical position. On the next try, the arm went down, but then it failed the grasp. Back to the drawing board. The LLM looked at the new failure images and realized the robot was pushing down on the cube while closing its gripper, which destabilized it. So it rewrote the code again to make the arm hold perfectly still during the grasp.
And did that work?
Third time's the charm. It worked perfectly. With just 2 rewrites, it went from totally failing to 100% success. They ramped up the difficulty with a task to pick up a can of soda and put it in a bin. First, the robot couldn't find the can at all because the code was told to look for a silver object, but in the simulation, the can looked red. The LLM saw this in the images and rewrote the vision code to look for red things instead.
That makes sense. A simple fix.
But then it created a new problem. The robot started moving towards the bin instead of the can. Why? Because the bin had a tiny red marker on it. The AI was averaging the position of all the red pixels it saw, and the little marker was pulling the target location off course.
That's such a classic programming bug. So how did the AI solve it?
It came up with a classic programming solution. It rewrote the code to not just look for red pixels, but to find the largest connected group of red pixels, which was, of course, the can. After that fix, it worked 100% of the time.
That's a pretty sophisticated level of reasoning. It's not just changing numbers, it's fundamentally changing the strategy.
It gets even crazier. For the hardest task, stacking one cube on top of another, the robot was consistently off by about 5 to 8 centimeters. After a few failed attempts at tweaking the controller, the LLM basically threw its hands up and said, the controller logic isn't the problem. The error is so consistent it must be a bug in the vision pipeline itself.
No way.
Yes, it actually figured out there was a bug in how the simulation translated 2D camera pixels into 3D world coordinates. It was a subtle error related to the coordinate system conventions of the graphics library being used, something that would make a human programmer pull their hair out. The LLM diagnosed it and fixed it.
That is truly impressive. It sounds almost too good to be true. Did it have any limitations?
It did, and the researchers are very upfront about it. On that hard stacking task, even after fixing the vision bug, it still failed about 9% of the time. The LLM correctly identified the reason. When placing the top cube, the gripper would slightly bump the bottom cube and knock it out of place.
So it knew the what, but not the how.
Exactly. It diagnosed the problem perfectly, but within its allocated number of tries, it couldn't come up with a code change, like a different angle of approach or a more gentle release that solved the problem. It got stuck. It's a good reminder that this isn't magic. It's a very clever, iterative problem-solving process that can still hit dead ends.
So what's the big takeaway here? Is this the future of robotics?
It's a really promising direction. Think about it. Instead of needing massive data sets and weeks of training, you could have a robot that learns on the job. If the lighting in a warehouse changes and a robot starts failing, it could potentially debug and rewrite its own vision code in a few attempts.
It makes AI feel less like a mysterious black box and more like a collaborator, a system that can fail, reason about its failure in a way we can understand, and fix itself, is a huge step forward for building more reliable and adaptable AI.
That's the core of it. Act, observe, rewrite. It's a simple loop, but it represents a powerful idea. What if a robot's best tool for learning about the world wasn't more data, but a text editor and a little bit of self-reflection?